Friends, welcome to the 17th lecture. We will continue with the damping estimate. In the last lecture, we discussed about damping estimates using Rayleigh damping method. We derived the equation, we solved the problem by hand, we also gave you the computer code and we validated the results by the computer code with that of the solution what we had by hand. We had exactly the same answers, more or less comparable for Rayleigh damping. Now, the second issue which is also related to damping in offshore structures is, if you really want to include higher modes in terms of damping ratios, then one should take a general form of classical damping matrix. Remember, classical damping matrix is assuming damping ratio more or less proportional to the same in all the modes, entire space of the structure. So, let natural frequencies omega r and phi r be known. They satisfy the following relationship. K phi r is omega square m phi r. Pre-multiply equation 1 by phi n transpose k m inverse on both sides. Okay, we get phi n transpose k m inverse k. I am just grouping it. Phi r is omega r square phi n transpose k phi r. This is equal to 0 for n not equal to r, because the modes are orthogonal. Okay. Pre-multiplying equation 1 on both sides by phi n transpose k m inverse square, we get phi n transpose k m inverse square k of phi r is omega r square phi n transpose k m inverse m of phi r. I have just expanded k m inverse square like this, okay, which is equal to omega r square phi n transpose k m inverse k of phi r. Please look at this equation, omega r square phi n transpose k phi r. Okay. Omega r square phi n transpose k m inverse k phi r. Okay. This term which is expressed here, phi n transpose k m inverse k phi r, phi n transpose k m inverse k phi r. Okay. This is already 0. So, I should say this is now 0 for n not equal to r. So, we are repeating this. By repeating this application or this procedure, we can establish a family of orthogonality relationships. Now, this can be expressed in general form as phi n transpose C L phi r is 0 for n not equals r, where C L is k m inverse to the power L of k for L equals 0, 1 to infinity. Now, C L can be rewritten as follows: C L is equal to k m inverse to the power L of k for L equals 0, 1, 2, infinity. Call equation 3a. Pre-multiply equation 3a with I, which is m inverse. So, C L is equal to m inverse of k m inverse L of k, which can be said as m inverse k m inverse, let us say k m inverse of L times of k, which can be m inverse k of L times of k, because I can group each one of them, and so on. This is true for L equals 0, 1, 2 up to infinity. I call this equation number 4. So, C L is equal to this equation. Similarly, for k phi r equals omega r square m phi r, pre-multiply the above equation by phi n transpose m k inverse. Follow the same algorithm as we did in the previous case. So, we get C L is equal to m inverse k to the power L for now L equals -1, -2, -3 to infinity, equation 5. So, now combining 4 and 5, equation 4 and 5, we get C L is m summation of L equals minus infinity to plus infinity, because in this case C L is valid in the minus range, in the previous case C L is valid in the plus range. So, combining these two, I can say C L minus to plus infinity A L m inverse k to the power L. It can be seen in equation 6 that only n terms in this series are independent. This shall lead to a general form of classical damping matrix, which is given by C L equals m L equals 0 to n minus 1 A L m inverse k to the power L. I call equation number 7, where n is the number of degrees of freedom of the dynamic system, and A L are constants for the damping matrix. Let us consider first 3 terms of this series in 7. So, let us say A 0, the equation is, I am considering first 3. So, let us say I am putting this as 0, 1 and 2 is starting from 0. So, C 0 I am interested. So, I let find out A L or A 0 into m, see A 0 into m inverse k, okay, m into m inverse k, right. So, m into m inverse k to the power 0, you can see here m A 0 m inverse to the power 0, okay, which will give me A 0 m. Similarly, I substitute this as 1. So, A 1 m inverse k 1, okay. So, A 1 m inverse k will be equal to A 1 k. Similarly, A 2 m inverse k square will be equal to A 2 k m inverse k. I call this as equation number 8. One can very easily see here the first 2 terms are same as Rayleigh damping, is it not? These 2 are same as Rayleigh damping. Suppose one is interested to specify damping ratio of J modes of n degree freedom system model, then J terms need to be included, and this series is what we call as Kage series. This series is what we call as Kage series. So, we include this in Kage series. So, there could be any j of n terms of equation 7. The equation 7 is this. There could be any j of n terms of equation 7. Typically, first j terms are included in the series, okay, and they will be as follows. C is going to be m summation L equals 0 j minus 1 A L m inverse k of L, equation 9. Then the modal damping ratio zeta is given by the following set of equations. Let us say for nth mode, we know the generalized damping is given by C n, which is phi n transpose C phi n, which can be now said as summation of L equals 0 to n minus 1 phi n transpose C L phi n. I call this equation number 10, where C L is m inverse k to the power L, which is same as equation 5 which we already had. Okay. Equation 5 m inverse k L same as that equation m inverse k L. Okay. So, for L equals 0 because it has to vary from 0 to n minus 1, L equals 0, phi n transpose C 0 phi n will be phi n A 0 m of phi n, because no, for L equals 0, okay, we already have this term is A 0 m. Okay. So, A 0 m is added here. Similarly, for L equals 1, phi n transpose C 1 phi n will be phi n transpose A 1 k phi n, which is actually equal to A 0 m n. This can be A 0 omega n square m n, and for L equals 2, phi n transpose C 2 phi n can be phi n transpose A 2 k m inverse k of phi n, which can be A 2 omega n square